then as you have seen, you can obtain a mining chip which does the computation 10 to the power of 12 hashes per sec. In a single machine, can redo the whole blockchain again if you don't have a PoW. Okay. So content in the blockchain cannot be changed. Why? Because of the heavy arrow. Heavy arrow here means there are a large number of consensus nodes, like millions of nodes in the Bitcoin case. They have put their energy to mine this block. Okay? They have worked together, right, at this time stamp, at the time that this block was mined. Okay? So that's that. And making PoW, that leads us to how to make PoW puzzles. We have seen this in previous lecture, but here more arranged setting. You will see what's going on. So here we have this hash output, but hash output is a number. So you can divide this set into two sets, right? One set is good, the other set is bad. Then basically, in order to find the good hash, which is a random mapping, in this case, if it's divided into half, then the probability of finding a good hash is half, right? If we divide this set into 4, then the probability of finding a good set, let's say, divided this into 4, and then the first set is 0, 0, the other set is 0, 1, and 1, 0, and 1, 1. And then let's suppose that that is the leading bits in the 256-bit output. Then basically if we say that the number of leading bits is equal to 0 is 2, then if we define that as the good set, then the probability is 1/4. How about if you have add one more bit? So 3 leading bits are 0, then the probability is 1/8, and so on and so on, right? So number of leading bits that are 0, we can control the probability of mining success. All right. So that's what it is here. But if you do that, what is the consequence? The probability of finding a good hash is going to get decreased by what? By half, right? Which is a large step. So in order to, can we make it continuous? So that's this effort here. Since that is a number, this fx is a number, then we can specify a binary number, right? If we, the output of hash is smaller than this target number, then we can make this, probability relatively continuous, right? Even though it is actually discrete, but we can make it look continuous. At least smoother than the step size of 2. Factor of 2, right? So for a block, find the nonce that satisfy the above inequality. So that's the mechanism that is actually used. Not the leading number of 0, but is this number smaller than the target number? Okay. And so here is an example with the 6-bit output compared to the 3-bit target. So basically you can read about it. And in the case of a Bitcoin, we can, so this is the case of 4 leading zeros. The probability is 2 to the power of 16 minus 16 and so on. But this is not continuous. So we want it to be, let's say, move on to, maybe in this lecture only up to that far. Okay, so that is the probability of mining success in a single hash. Okay? If you run single hash, what is the probability of success? Okay? So given we can call it as a difficulty level. Okay? So because that's the probability. If the probability is small, then you can say that difficulty is very large. Okay? And then we aim to find the probability of mining success. Now we want to define a random variable k. Random variable is just a representation of your experiment. And then let k 1, 2, 3 denote the index of the hash at which PoW success occurs. Okay? So here I am saying what is the probability of mining success at the kth hash cycle. Okay? So for example, k is equal to 4 means that PoW success comes exactly at the 4th hash. So what does this mean? In previous first and second and third, there should be failures, right? Hash failures. The previous hash output land in the bad set, right? So what is that probability? Probability of success in a single hash is P. If you use this notation, then probability of hash failure for a single hash, right, is 1 minus P. You see? This is just like flipping a coin. You get the top with the probability of P. You get bottom with the probability of 1 minus P. Right? And then what I'm asking, what is the probability of selecting good hash at the kth hash output? Okay, then all k minus 1 hash output should be failures, right? First one, failure, and second one, failure, and third one, failure. So this and here means multiplication in probability. Okay, so that's what I have, and then that's the geometric distribution that we have, okay? All right. All right, so here, where is this? So here, this, since my note doesn't have that, let me see. So what I just said here is that probability of, what is the notation? K, okay. Random variable K, here this one is exactly at this hash cycle, I have a success. That's what the capital K represent. And the small k is, let's say, is equal to 4. Right? What is this event? That event should occur, what? 1 minus P, first one. Another 1 minus P, second one. 1 minus P, third one. Right? And then right at the 4th cycle, there I have a success, P. So that is this, that is that. And then what if I do with less than or 4? Then I have to include first success, second success, third success, and so on. Okay? That is this formula that I'm getting here. Okay? So this is the probability that k is equal to 1. This is the probability that k is equal to 2. And then this is the probability that I have here, right here, right? K minus 1 failures, and right at the last moment, I have a success. Okay? So that's the k smaller than or equal to k, smaller k. Okay? When k is equal to 100, then there is nothing but 100 times p. Okay? So this is like, you flip the coin 100 times. What is the number of, ones? That type of thing. So that is 10 times p, and so this is the geometric distribution in the in the probability theory. And let's now go back to this chart here. Hash rate. Now we want to define hash rate. So how many hashes a CPU can generate in a unit time? Okay. So hash, that's what we call hash rate. The hash rate of a CPU, which can do 100 hash cycles in 1 second, is 100 hashes per sec. That's the definition. Okay. And there is this mining machine, mining chip, does 14 terahashes per sec. So tera here is 10 to the power of 12. So, and then the price is $3,000. Okay, but this was back in 2019 when I was developing my lecture notes then. Okay, so currently maybe it has gotten cheaper because electronic price always get cheaper as the year goes on, and then performance gets better, right? Each year, right? All right, and then here, 시간이 됐나 벌써? 가방 싸는 소리가 들리는 걸 보니까 너무 많이 했나 보네. So basically, I'll stop here. Then, since the time is up, and I want you guys to take a look at this part and then start doing the homework. Okay. All right. So, do you have any question? If you have any question, you can ask me.